So we're going to evaluate the centroid of the area of this composite shape. And the centroid of the area here, or for any shape, it's simply the point where the area would perfectly balance if this were to be a thin uniform plate. And the best analogy I can give you is when we were looking at finding the moment for different beams or the reaction forces, what we had was, let's say we have this beam and we have a pin joint there, let's say a roller there. But what we had in terms of loads, we had this UDL, so that uniformly distributed load. So that's representing my UDL. And let's say this, for this UDL, it should span across, let's say 2 meters or 4 meters. So it spans across 4 meters. And in terms of the actual UDL measurement, let's say it's representing 2 newtons per meter. And what we did with this was to convert it into a point load. So we multiplied the 2 and the 4 to get that as 8. And we focused that 8 newtons right there in the middle, because that's where it will have the maximum effect. That's where the center of gravity will be most dominant. So it's kind of similar here for the centroid of the area. We're trying to find or to locate that point in this system or this composite shape where the shape could be balanced perfectly at that point. And to do this, we're going to organize the information on a table so you can clearly see what we're doing. So in terms of the headers, we're going to have to break this shape down into different components. So what the components will represent, they are just going to be the different shapes that the composite shape here is made up of. And then what we'll need to do, we need to evaluate their different areas. And we'll just keep the millimeters, so we'll use millimeter square there. We're going to find their relative distance from our axis. So that's our X bar. And we'll have the same thing for Y bar right there. Then in this column, we're going to multiply our X bars by our area. And that's our millimeters square multiplied by millimeters. So our unit there will be millimeters cubed. And we do the same thing for our Y bar multiplied by our area. And the unit here again will be millimeters cubed. So let's break this down now into our different shapes. So you can perhaps see that we have 4 different shapes. So let's start by looking at our first component, which is, I'm going to start with the rectangle. So for the rectangle, you can see that dimension right there. That's 80 millimeters. And it will go across its width right there, which is 120. So for our rectangle, I'll just short spell that out, RECT. That will simply be 120 multiplied by 80. And that's going to give us 9,600, but I'm going to write it in standard form. So 9.6 times 10 to the 3rd power, and that's millimeters square. Now to get the X bar, Y bar, that's going to be based off of our axis. And we have our axis located, so you can see I've circled the Y axis there. I've circled the X axis there. And the X bar, Y bar for rectangle is just simply base divided by 2 and height divided by 2. So we already know our length along the X axis, and our length along the X axis, that's 120. So if we divide that then by 2, then that's why we're going to have the 60 millimeters right there. And for Y bar, that's going up in the positive direction up to 80. So when we divide that by 2, we end up getting 40 mil. So what we do next, we're going to do X bar times the area, and X bar times area, which is 60 times 9.6 times 10 to the 3. That's going to give us 576 times 10 to the 3rd power there. And for Y bar times our area, when we do 40 times 9.6 times 10 to the power of 3, that's going to give us 384, and that will be multiplied by 10 to the power of 3. So that takes care of our rectangle. And now we're going to go to our triangle, which will be quite an interesting one. And I'll tell you why that is so. Now for the triangle, if we look at our X and Y axis, we know that all the values going up right here, that's gonna be positive. All the values going to the right, that will be positive as well. So what that means, our triangle, it's positive in the X direction, but it will be negative in the Y direction. So I'll show you how we'll have to treat that. So we're going to go next to the triangle. So for the triangle, our length is going to be 120 and our height, it's going down 60 in this direction. So that's the 60 there, and the 120 is still going across. And we do half the base times the height for the triangle. So that's half multiplied by 120 multiplied by 60 for the triangle. And that will give us 3,600. So we'll just write that as 3.6 times 10 to the 3. So we're going to get our X bar, Y bar for our triangle now. So for the triangle, our X bar, Y bar will be different. So for this one, so that's for the triangle. So for this one, we're going to be doing the base divided by 3. And we're also going to do the height divided by 3. So when we go to the X bar, it's going to be 120. That's divided by 3. And that will give us 40. Now when we go to the Y bar, this 60 millimeters, that's going down. It's below the X axis. So it means that that vertical length, we are going to use a negative value for that, which is crucial. So that's going to be 60 mil divided by 3, which gives us 20. But we have to have that as negative 20. So that's very important there. And that's all in reference to our axis that we're using there. So from there, we just need to multiply our X bar times our area. And when we do X bar times area, so that's 40 times 3.6 times 10 to the 3, what we end up with is 144 times 10 to the power of 3. And onto the Y bar, so what we have here is negative 20 times 3.6 times 10 to the 3. And what we end up with here, this has to be negative, so it's negative 72 times 10 to the 3. So that's one thing that we need to be very mindful of. So I'm going to go to the semicircle next. So for the semicircle, so we know the area of a circle to be pi r squared. And this is simply a semicircle. So we're going to end up with half times pi times the radius squared. And we can see that the radius for this semicircle is 60 mil right there. So all we have to do is half multiplied by pi multiplied by our 60 squared. So we get that as 5.655 times 10 to the 3. So in terms of our X bar, Y bar for our semicircle, so I'll just put that down there. So for our X bar, we're just going to have R for radius. And for our Y bar, we're going to have 4R divided by 3 pi. So that's the formula that we'll use for the Y bar. And what we have now for the semicircle, X bar, that's just our radius, that's just 60. But then Y bar, when we work that out, we end up getting 105 and 0.46. And all we have to do next is just to do our multiplication, X bar times area, and that gives us 339.3 and times 10 to the 3, and Y bar times area, that gives us 596.4 and times 10 to the 3. So that leaves us with only one more shape, and that's our semicircle. And as for our semicircle, it's a cutout, so we're going to have that area subtracted. So we're going to use that as a negative value. And for circle, it's pi r squared, and we can see where that radius there is 40 mil. So we're going to have minus pi times radius squared, so 40 squared, and y minus is because that shape is cut out. So what we get for this is negative 5.027 and times 10 to the 3. So I'll go back up just to analyze the x bar, y bar for the circle. And for the circle, we need to be very careful here because in this instance, yes, our x bar, y bar will be the radius, but that's going to be according to our reference axis. So if we go across here, so up to this point, that's representing our 40 mil. But we need to go all the way across to the axis. So that's going to be representing 60 mil right there. And then now if we go along the vertical axis for y bar, so if we go from here to the edge of our cutout circle right there, then yes, that's 40 mil. But we need to take it all the way down to that axis right there, which will be 80 mil. So that's the idea. That's how we treat this. So what that means then, that means our x bar, y bar for the circle will be 60 mil for the x bar and 80 mil for the y bar. And with that, we can do our multiplication. So when we do x bar times area, what we end up with is minus 301.6 times 10 to the 3. And then for y bar, it's minus 402.2 times 10 to the power of 3. So there are some columns that we need to sum now. So what we're going to do, we're going to sum our area. So the sum of our area here, that will give us our 13.828 and times 10 to the 3. We're going to sum our x bar, and that will give us 757.7 times 10 to the 3. And finally, we need to sum our y bar, and that gives us 506.2 and times 10 to the 3. But we're not quite there yet. What we have so far, we have the sum of our x bar, we have the sum of our y bar, and we have the sum of our area. So let's see what we need to do with them to get our coordinate. So to get our x bar coordinate, then all we have to do here is just to do the sum of our x bar times area and divided by the sum of our area. So what that will look like now, that's our 757.7 times 10 to the power of 3, and all divided by the sum of our area, which is our 13.828, and that's times 10 to the power of 3. So it turns out that our x bar is 54.8 mil. So that's representing our x bar, and we move on to our y bar and we do the same thing. So for y bar, that's going to be the sum of our y bar times area divided by the sum of our area. And that gives us 506.2 times 10 to the power of 3. And that divided by 13.828 times 10 to the power of 3. And we end up with y bar as 36.6 millimeters. So that's our x bar, our y bar. So in terms of that location, that's going to be somewhere, I'll say somewhere around that mark there. So somewhere there, that's our centroid of the area.